The simplest version, it's called the complex field, you can represent by having a clock face at every point with one clock hand. So instead of a number like 20 degrees, you have a clock which has two properties. It has the length of the clock hand and the time. Actually, in basic quantum mechanics, that's how you describe things. And the square of the length of the clock hand describes the probability you'll find a particle at a point. So it's just a kind of a more abstract field. Now, that's concept number one. So that's what these are, a complex field, fields that describe a particle, little clock hands at every point in space. Then there's the idea of symmetry. So symmetry is really easy to think about. If you like a sphere, like a ball, then it has symmetries. I can turn it through different angles and it looks the same. That's the symmetry of a sphere. A mathematician would say that's what you need to describe a sphere, to characterize it. Something that you can turn to any angle and it looks the same. Equations are the same in math, a bit more abstract, but a very similar idea. The idea is, can I do something to these, the things that are described by the equation, like rotate them around, so the equation remains the same? If you can do something like that, then it's important, it's interesting, it characterizes the equation. The symmetry we're interested in with particles, something called gauge symmetries. Remember I said those force carriers are called gauge bosons, so you're going to see why, you're going to see where they come from. So think of a symmetry operation on these clock faces. So I've got my little clock faces at every point in this room describing the quantum field. So one symmetry will be, I'll change the time on all the clocks by the same amount. I'll go about 10 minutes to everything. Rotate them all around by 10 minutes. This equation is symmetric, it turns out, other than that. It's called a global gauge transformation. Fancy idea. This is where gauge bosons is going to come from. So that's fine. But then, because physicists are kind of curious, back in the 1920s and 30s, they said, well, all right, that works. So what happens if I decide to do a local symmetry? That means I'm going to allow myself to change the time on every clock face, but by a different amount. So I'll do 5 minutes over there and 10 minutes over there, and maybe I'll take 7 minutes off that one. I'll just twiddle all the clock faces around. Does that work? So that's what's called a local symmetry transformation, different at every point. Well, it turns out that it doesn't. And this equation that describes the non-interacting simple particles does not respect that symmetry. So what the physicists did in the 1920s and 30s was say, well, I'm going to fix it up, just mathematically. What do I have to do to this equation to make it respect that symmetry, that local symmetry change or transformation? And it turns out there's only one thing you can do. It's absolutely prescribed by the demand you make on these clock faces. And it turns out that you have to add a bit in. And this looks like a tremendous mess. But it isn't a mess, it's a fascinating mess. The bit you add in, is these bits, these A's, right? So you add a bit there, and this bit, which is some other combination or function of these things called A's. These are new quantum fields. And they're in fact photons, they're force-carrying particles. And in fact, this equation is precisely the equation that describes a theory called quantum electrodynamics, which is electromagnetism, the quantum version of electromagnetism. So Maxwell's equations, some of you might remember them back in your physics degree, describe Faraday's law and Ampere's law and all that, is in there. And they're forced into it by the demands of the symmetry transformation. Absolutely magical, quite bizarre. And it turns out the other two forces, the quantum force, the strong force and the weak force that operate in nucleus, also can be generated precisely by slightly more abstract transformations, symmetry transformations in these quantum fields. So that's the first message really. It's kind of, you're not supposed, obviously you can't quite, you'd have to do a lecture course to do it in detail, but the basic point is that the form of the equations that describe the forces of nature are built, are given to us for free by demanding these little symmetry transformations. Absolutely beautiful thing. Except, and this was noticed back in the 1940s and 50s, if those photons, the force-carrying particles that are generated by this process, if they have a mass, then this doesn't work, it stops working. This symmetry argument as an idea breaks down and mathematics doesn't work. And, experimentally, the W and Z particles that are associated with the weak nuclear force, the beta decay, etc., are massive, as I said, 90 times the mass of the proton. So it fails. So what can you do? Well, this is where Peter Higgs and others came in the 1960s, actually taking ideas from other areas of physics. There is a way that you can preserve this beauty and get masses for the force-carrying particles. And I'm going to show you what it is, because it's weird and strange, and it's called now the Higgs mechanism. So this is that again. Right? And all I've done is I've added a couple more terms into the equation. This is a mass term. Remember I said that that describes a particle with mass m. This describes a particle with mass u. Still down, mass term. And this term describes an interaction, a simple interaction between the particles. So it looks like I've done nothing really. I've just added a couple of bits of extra stuff into the equation. But then you do something very, very odd indeed. You say, I'm going to allow this mass squared here to become negative. M squared is negative. So the mass, you have to get the square root of the negative number to get the mass. You know a bit of maths, it's a complex mass. I times something. Weird thing to do. So completely unphysical. And then you change this, so it's not really describing particles anymore. It turns out it's describing what's called a potential. And this is a very famous potential called the wine bottle potential. And it has a very strange property. So remember, this is a graph. These are fields. These are phi, so these are those fields. Right? The origin of the graph is where the fields are zero. So that would be no particles. Empty space is empty. Nothing there. But that, in this weird case, is a maximum of the potential, a maximum of the energy. Now, as you know, in physics, systems don't like to be the maximum energy. It's like having a ball at the top of the hill. You don't want to get top of it, it wants to roll down into the valley. This, the idea is what the universe did. So the universe got itself into a state where such a field was present just after the Big Bang, way less than a billionth of a second after the Big Bang. This mass goes negative, it goes imaginary, complex, also called tachyonic, because it describes particles that appear to travel faster than light. Very strange thing. So the universe gets into this state, and then it rolls down into the valley, into the lowest energy state. Right. This is the Higgs mechanism. It does something very strange and very magical. What you do, just mathematically, is you say, well, this physical system is a bit weird, it's up here, so I'm going to translate it down into the real vacuum, the place where the energy is minimum. That's the place where these fields are non-zero, see, it's up there. So this field now has got a value. So really, physically, what you're saying is the universe goes from a state which is all very beautiful and symmetric, but high energy, rolls down into a space which is less beautiful and not symmetric anymore, but lower energy, and fills itself with stuff in the process. That's called the Higgs condensate. So this is where Higgs particles come from in this theory. The universe, the Higgs crystallise out, condense out into the vacuum of space as the universe expands and cools in order to get the universe down here. Interesting, kind of a bit weird, but interesting. So what you do mathematically, you take this equation and you move it, you shift it down into here, just mathematically add something to it to get it into the place it should be. And when you do that, and this is the last bit of the complex stuff, you get this equation. And this is really fascinating because here are the photons, the force carriers. Here is something squared, it's a mass term. Right? It's a mass term that depends on the shape of this and the strength of the force. So the photons have got mass, the force carriers have got mass by the universe rolling down into here. And this is another term with another mass term, which is written a bit differently, but it's still something squared times some numbers, mass. That's the Higgs particle with a mass that's predicted by the theory. So by doing this strange thing, by performing this just mathematical aesthetically pleasing dodge in order to keep my symmetry stuff all working, I end up generating a mass for the force carriers and a prediction of another massive particle which is sitting there to be discovered. And this is the Higgs mechanism. And if you just look back finally at that big equation that I showed earlier, you can see all the bits. So here are the Higgs bits, which are there, and here are these bits, which come from the symmetries and the force carriers, and here are these bits, which look like those bits. So all of these bits, every bit of that equation is generated by some kind of nice mathematical idea, but it's got this weird consequence. You're not allowed to do this. For mathematical reasons, I end up with a prediction. I've got massive photons, massive force carriers, and I've got these things left over from the symmetry breaking process, which are the Higgs particles. And so that's what we went to look for. Abstract, but fascinating. So we build then with the world's largest experimental collaboration for a start, 88 countries from around the world, including on one of the experiments, I always find wonderful, America, Iran, Pakistan and Israel working together on the same experiment. Remarkable thing. But you get 88 countries from around the world and build the most complex scientific experiment ever built. 27